Okay, let me give you a review on how to solve the differential equation using Laplace as we discussed on Thursday class. So we take the y double prime plus y equal cosine 2t, okay? And we have the conditions that is this and one more because it's second order. So we need two initial value. So we have that. Okay, so we take the, let me write, copy, okay, and then take this to the left. Okay, so we take Laplace, and take Laplace of the right side of equations. So the y double prime becomes x squared, and then become y capital, s, okay, and then minus s y 0 minus y prime 0, and then y becomes capital Y s, right? And then the cosine becomes s over s squared plus 4, right? And then we take the conditions, that is when 0, it's supposed to be 0, and when y prime is at x0, it's equal to 1, so this will be 1, okay? So nothing really complicated here. So we could just take this -1 plus this, and then we have this. Okay, now what we need to do is we take the solving for capital Y, right? And then we have 1 plus s, and then we write the y 1 over s squared plus 1 plus s over s squared plus 1 s squared plus 4, okay? Now if we combine this, and let's say we are going to use partial fractions, I think we can just focus on here, okay? So we could write this, and we could partial fraction this part, okay? And it's equal just s, okay? S cubed plus bs squared plus 4as plus 4b plus cs cubed plus ds squared plus cs plus d equal s. So s cubed a plus c is b plus d, 4a plus c, and then plus 4b plus d is s, okay? So a plus c is 0, 4a plus c is 1, so we should have, okay, this will be 1 over 3. So c will be -1 over 3, and b plus d is 0, and 4b plus d also 0. So b is all 0, right? So b and d is 0, so we could have the result as 1 over 3 s squared plus 1, and -1 over 3. I think this will be much better, s squared plus 4, this will result in sine t, but let me write the cosine and well, I think, okay, maybe sine t, and then plus 1 over 3 cosine t minus 1 over 3 cosine 2t. Okay, that's a good example. Okay, so the key is the partial fractions. Okay, we have learned before the translation theorem. So whenever we have the translations of some point A, which means we are going to translate this f of s to f of s minus a, it means that we are actually multiplying the function with an exponential function with power of a constant t or at. Okay, so this constant will be the units that is going to be shifted. Okay, because we can prove that through the definition of Laplace, and we know the Laplace itself is an integration of the exponent. So it is, I think, makes sense that if we multiply with an exponent, which means that we are going to plus or minus the graph, or the graph. Okay, we're just changing the horizontal position, and that's why we have these conditions that when we have these conditions, what we are going to do is we are going to evaluate the t cube, so Laplace of t cube, and then based on this 5 we are going to translate s minus 5. Okay, so we get this first and then translate this as, substitute with s minus 5. Okay, same thing with this. Okay. We can translate, and we can start with the cosine 4t and then translate to plus 2, right? Translate to like that, and this is become as s squared plus 16, right? This is the cosine 4t, but we need to translate this to s plus 2, so we change all s with s plus 2, so it becomes s plus 2 and then s plus 2 squared plus 16. Okay, again we give more example. Or maybe we take the inverse first, and then we can have more examples. So the inverse form of translation. So Laplace inverse of f s minus a, this will be Laplace inverse of f of s. Okay, and then we could say the s to s minus a like that. Okay, and this will be equal to e at ft. This is just reversing the process. Okay, where ft is equal to Laplace inverse of the capital F s, like that. Okay, so example for this inverse is example. Okay. This is Laplace inverse of 2s plus 5. This will be s minus 3 and then squared. Okay, what will be? Now to begin with, we could think just the fractions and then take the partial fraction. I hope you still remember partial fractions. This is we call the repeated linear factors. So this s minus 3 squared is a repeated linear factors. So we could take this s minus 2, s minus 3, sorry, and then plus the other one is s minus 3 squared. Why we need this becomes like this, not just like s minus 3, s minus 3, because we want to make sure that the upper coefficient is just a constant. Okay, We have already discussed this on the calculus, so if you feel confused, go back to your notes, okay? Go back to your notes. All right, now we are going to check the constant a and b. So let's check. A is s minus 3 squared, or we could take this s minus 3, just s minus 3, okay. And then plus b is equal to s plus 5. So SA minus 3a plus b. So we know that the a is 2 and minus 3a plus b is 5. So b is, so minus 6 again plus 6, it's 11. So we could have the Laplace inverse of 2s plus 5 s minus 3 squared, okay. So this will be Laplace inverse. Let me write all together. S minus 3 plus 11 over s minus 3 squared, okay. Now this part we can make one by one. I think we can take this 2 Laplace inverse to 1 over s minus 3 plus 11 Laplace inverse 1 over s minus 3 squared, right? And then what will be, okay, maybe let me use different color to give you notes. Let me write here. So Laplace inverse of 1 over s minus 3 squared, okay, what will be? We can think this in the original terms. This is coming from, maybe from here, right? From 1 over s squared, which means this is actually Laplace inverse of this. It's just t. But then it's going to be s minus 3. So we are changing from s to s minus 3, which means that this is actually changing from t, okay, to 3 units to the right. So we could say that this will be e with power of 3t and then t. So remember, when we have this e, which means we are going to translate, okay, translate from s to s minus a constant. The constant is 3, okay? So this part here is e to the power of 3t multiplied by t. Okay, and then we could take this. The first part is, I think, very simple. 1 over s minus 3 is just e with power of 3t. So 2 e power of 3t plus 11 e with power of 3t multiplied by t. Okay. Well, we could factor out this 2 plus 11t. Okay. That's the example. Okay, maybe another example. Laplace inverse of s over 2 plus 5 over 3 is a little bit awkward fraction, but let me just write first. S squared plus 4s plus 6. Okay, I think we need to try to look at this equations. Perhaps we need to do something. Okay, we need to rewrite this algebraically. Okay, so perhaps we could see maybe from the denominator first. Can we maybe rewrite this in a complete square? So perhaps if we have this s plus 2 squared, well, it should be plus, if we square this should be 4, right? Plus 4. So we need to plus 2. So we could change this with this, right? Okay, and now, okay, what we are going to do next is we are going to see that maybe this equation has something to do with s plus 2. Okay, we've tried this. So first is the s over 2, this part here. If we try to take the take half, s plus 2, okay, what will be? It will be s over 2 plus 1, right? Plus 1. So 1 and 5 over 3, I would like to take that as 3 over 3, or 5 over 3 minus 3 over 3. So we could write down this part becomes Laplace inverse. So we are forcing out all the fraction having this s plus 2. Okay. So this will be half s plus 2 plus 2 over 3. Okay. And now, by looking at these equations, let me write with green color. So we have half s plus 2, s plus 2 square plus 2 plus 2 over 3, 1 s plus 2 squared plus 2. Okay. So this is, I think we can just write the Laplace. Laplace inverse of all this. Okay. And then we could take half Laplace inverse of s plus 2, s plus 2 squared plus 2 plus 2 over 3, Laplace inverse 1 s plus 2 squared plus 2. Okay. And now we could take this and we could write like really taking times to make sure that we understand. And imagine this is s, this is s, this is supposed to be the cosine, right? So we could say this will be Laplace inverse of s over s squared plus 2, and then we shift it from s to s plus 2. Okay, and then plus 2 over 3, and we could also because we have 1 and this is 2, so we need to make sure that this constant 1 is multiplied with square root of 2. So we need to take that square root of 2 down here. And we say that this will be from s to s plus 2, right? So we shift it to s plus 2. So this will be half. And then shifted s plus. So plus means that we have e with power of negative 2t. Okay. And then cosine square root of 2 and then multiply by t. And then plus 2 over 3, or maybe we could rationalize this. So square of 2 of 3, okay, and then e with power of negative 2t sine square root of 2t. Okay, that will be the answer for the inverse. Okay. Okay. Okay, now how if we try to do some examples related to initial value problem. Okay, now let me write example. So solving the y double prime okay, and then we have two constrictions, two constraints like this. Okay, at this part here, if we observe carefully, it's similar to what we have in which one? Which example? Wait, let me check. Example, or maybe we could take that later on. Okay. Well, oh, this will be, I think, this example. Oh, yeah. Pretty similar for the I think this part, right? This part here. Similar, but it's 2 and 3D. So we could imagine that this is going to be pretty similar. So we are going to take Laplace for all these differential equations. So we write Laplace of y double prime Laplace of y prime and plus 9 Laplace of y and Laplace of the right hand equation, which is t squared e 3t. Okay, now we could try to take each form of Laplace. Okay. So y double prime is becoming s squared and then capital Y and then minus s y of 0 minus y prime 0 and then minus 6, and then y prime becomes, let me use brackets to make it more organized, as ys minus y of 0 and then plus 9 y capital of s and then equal. Now this would be 2 factorial, okay, over s cubed, but we are going to shift it, this s to s minus 3 based on this 3 here, right? So this will be 2 over s minus 3 and then cube. Okay, and now we can simplify all of this. So taking the y capital S, then s squared minus 6s, okay, I think we have done this part, and then plus 9, right? Plus 9. And then this will be y0 is 2, so this will be 2. Y prime 0 is 17, right? 17, okay. And this will be 2. Okay. So 2, this is 2s, negative 2s. Negative 17. Negative 6, negative 2 is plus 12. So negative 17 plus 12 is negative 5. So we are going to have 2s plus 5. We move to the right side. And then plus 2 over s minus 3 cubed, right? And then what should we do now? I think we can simplify this. This is s minus 3 squared, right? So we could take that and divide all with s minus 3 squared, okay, and then plus 2 s minus 3. Now it's from cube, and then plus 2, it's 5, okay, it's 5. Now I think we could separate this by taking the partial fractions. So I think I will take that in maybe this like small part here. Let me write here just to make you remember how to do this, some partial fractions. So this will be s minus 3 plus s minus 3 squared. This is a, this is b. So we are going to have a s minus 3, right, plus b. Okay, this is 2s plus 5. So as minus 3a plus b. This is 2s plus 5. So a is 2. And negative 3a plus b is 5. So negative 6 plus b equal 5. So b is 11. So we could take that into our equation here. That we are going to have 2 over s minus 3 plus 11 over s minus 3 squared. Okay. And then plus 2 s minus 3 with power of 5. So we could have this part, or maybe let me just write here. And then taking the small y, meaning we are going to take the Laplace inverse. Taking Laplace inverse, it should be 1, sorry. 1 over s minus 3 plus 11 Laplace inverse. 1 over s minus 3 squared. And then plus 2 Laplace inverse of 2 over s minus 3 with power of 5. This is not 2, this should be 1. Okay. Okay, now I think for the first two, for Laplace inverse, no problem. We could do directly. But for this s minus 3 with power of 5, remember when we have this 5, the upper level should be n minus 1, right? So 5 minus 1 factorial. So we should have 4 factorial. So we need to divide this by 4 factorial, okay? So, okay, we can take that as, maybe let me write some in red color to make sure we are correct. So Laplace inverse of 1 over s squared, right? And then shifted from s to s minus 3, right? So we could write 1 over s squared is t, and then this s minus 3 is e with power of 3t. And then Laplace inverse of the four factorial over s with power of 5 is s, and then shifted to s minus 3. Or we could write t with power of 4, and then the shifted is e with power of 3t. So in total, we could have yt is 2 e. I think no problem for the first one. And then plus 11t e with power of 3t, right? And then plus 2 over 4 factorial, or 4 factorial is 4 by 3 by 2 is 24, so 1 over 12, right? 1 over 12. And then t with power of 4, e with power of 3t. Okay, that will be the final results, the solutions. Okay. Okay, the next sections will be about the unit step functions. Okay, the unit step function, or we call also the Heaviside, or we call the Heaviside function. Okay, Heaviside is not the terms like special term. It's special term, but it's actually coming from a person. So he invented this function. So what is unit step functions? So in engineering, like when you switch off some power grid or just like a normal lamp, well, we are going to encounter, like in engineering, that functions that has those characteristics, which is off and on. And to illustrate what happens, let me just give you a graph, okay, that illustrate what is happening. So if we have this is what we call the Heaviside function. So what Heaviside function means is at some point A, at some constant A, let's say we have the t-axis for our variable, and the function is the Heaviside. We call this Heaviside to make it easy. Okay. Now, what happened is when we are moving from, let's say, from the origin going forward to some A, it's still all in 0, right? But suddenly it jumps, right? It jumps. And then suddenly from this interval, from the A up until we, let's just say t is greater or equal A, then it's equal 1, okay? So we could write down in the Heaviside, or usually it's more likely to be having more curl like that, okay? So t minus A, or we could write these functions like this. This will be equal to, let's write in piecewise, 0 and 1, okay? So it's equal 0 if the interval is from 0 to A, but not including A, and it is equal 1 if you have t greater or equal A. And this will be the definitions for the unit step functions. Unit step function. Okay. So we need to make this unit step functions more practical, okay? So when a function defined for t greater or equal 0 multiplied by this unit step function, then the unit step function, it will turns off a portion of the graph of the function. Okay, so let's say, imagine we have just a functions ft 2t minus 3. Let's say we have this, okay, just a line equation, normal equations. And we know that if we draw the curve, we just draw the okay, let's say this would be 2t minus 3 is around, let me take this 1, 2, 3, 1, 2, 3. Okay, supposed to be from -3 from down here, -3, and then when it's 0, it goes to be 3/2, so maybe around here, the intersections and the intercepts. Let me write with the red color. Okay, let me draw for you. Okay, this will be the line, right? This will be the line. So we call this our functions, right? 2t minus 3. Now, if we multiply this function, if we multiply with the unit step functions, okay, unit step functions. So let's say we have a new set of functions, or let me just write 2t minus 3, okay, and then multiply with the unit step functions t minus 1, let's say minus 1, okay? So what does it mean is, because of this, okay, t minus 1, when t equal 1, remember when t equal 1, it will be 0, like this part here. When t is equal a, it's equal 1, right? But when it's less than a, it equals 0. So what does it mean? It means that from 0 here up until 1, the line will be turned off. So we could draw this like this. So we just erase, and then there will be some jump here, okay? And this will be the curve, or maybe if I take the original picture from the book, this will be the curve, okay? Right? So simply, because we know that this will be 2t minus 3, and this is the turn off, the interval that is turned off, and this is 1, we know that this graph is 2t minus 3 unit step function, or mu. It's more like having a more curve like that, yeah. T minus 1. Okay, I hope you get my idea. So if we could write f of t, if we write into two pieces, let's say we call another function g and h, and there will be different interval. So this first one is from 0 to a. So we are always taking the interval, okay, from 0, not from the negative sign, okay? And this part is t is greater than a, and we need to have some constant a to make sure that we have these two distinct on and off, okay? We could write the f of t as g of t minus g of t multiplied with the unit step functions t minus a plus h of t, and then it's not curly enough, I think that's better, and then t minus a, okay? I hope you get the idea, okay? The idea is coming from the one that you are multiplying with the original functions. So you have some unit step function to be multiplied. For example, we have this to be multiplied with this g of t. This is the first interval here, okay? And then we need to also multiply the step functions, multiply with h, this for the next interval here, right? And this will be equal to f of t, okay? So f of t is g of t minus all of this and plus the h of t, right? For example, we have the f of t. Well, we could also write more than one constant. For example, we have 3 intervals. For example, 0. Let's say 0 is from 0 to a, and then we have another function g, and this is from a to some constant b, and another point maybe 0, and then we say that this will be t greater or equal b, okay? We could also write this similarly, because it's 0 having 2 0, we could write usually we need to take this g of t, but since it's 0 for the first interval is 0, so we could directly write g of t multiply with the unit step function t minus a. Okay, and then with a bracket, and then minus the unit step functions t minus b. Okay. So this is, I think, very good example to illustrate how the Heaviside function works. Okay. Now for this part here, the example for the picture, what we can have is, for example, this one. Okay, this is f of t is equal to, okay, you can see 2 is the maximum value, minus, okay, 3 unit step functions t minus 2. Okay, let me draw. This is 2, this is 3. Okay, this is okay, I think that is just the important one. And then plus the unit, let me write clearly, unit step functions t minus 3. Okay. Okay. Okay, I think could wrote another example. Let me get to the next example. Okay. So let's say we have f of t so express f of t in terms of unit step functions. So we take this 20t as our, let's say, g. Suppose let g of t is equal to 20t and h of t is 0, right? So what we could have for f of t, as we mentioned before in previous slide, this will be g of t minus g of t, and then the unit step functions t minus 5. Okay. And yeah, I think we could imagine that for this graph, it will goes to like going up like that until it's 20t from 0 to 5. So it should be like, maybe this is, if this is 100, then this will be 5, and after this 5, this will be equal to 0, right? This is t, this is f of t. Okay. We could express, so maybe consider the general functions y f of t, define for t positive. Okay, and we could write the f t minus a, and then unit step functions t minus a, this will be equal to 0, and f t minus a 0 less equal less equal t less t, and t greater equal a. Okay, this could be plays significant role in the next discussion. Okay, we are going to move on okay, to the second translation theorem, okay, from this statement here, okay. Okay, to give you an overview on how to use the unit step function or Heaviside functions in terms of Laplace transform, let's say we are going to evaluate the functions that are given in previous example here. Okay, so we have these functions f of t in terms of the unit step functions as 2 minus 3 is step functions, t minus 2, right? This is 2, and then plus the step functions t minus 3, okay? So this is 3. So let's say we are going to get the Laplace transform of this. So let me write. So Laplace transform of f of t. So 2, we can just write 2 and then Laplace of 1. And then plus 3. Now Laplace of unit step function. So you have two different curly units, the Laplace and Heaviside. And then t minus 2. And then plus Laplace of the unit step function t minus 3. Okay. Now this part, okay, 2 over s, nothing really complicated. But for this one, if we remember what we have in previous examples here, we could directly write this unit step functions, okay, let me write with this unit step functions t minus a. So every time we have this, since we have this these relations, we could write this equaling to this part. So we could write the Laplace itself as the e to the power of negative as over s. Okay, so we could write down this part here. So plus 3 multiplied with e power of negative 2, right? Negative 2 s over s. Okay, and then plus this is negative 3, so e negative 3s over s. Okay, and we've done the Laplace transform. And now, how about if we take the inverse form? Okay, so we take the inverse. So the inverse of e with power of negative as of the capital F as. So this is supposed to be the form that already have been Laplace transformed. Then we could rewrite this, and we reverse the process and take the f t minus a and a unit step function. Unit step functions like that, and t minus a. All right. Okay, now let's go take a look some examples. So Laplace inverse. Okay, how about that? So we could identify first that this is our a. So negative 2 is or 2 is a, because we need to remember that the original expressions is with negative a here. Okay, So if it's already been in the negative form, then a is 2. Okay, so we could write that the f of s, the couple of f is this. Okay, maybe before we take our final results, we take this f, the capital F as. Okay, so take the Laplace inverse of 1 over s minus 4. Okay, this will be e with power of 4t, right? And then we are going to multiply with this e, which we are going to multiply with the Heaviside functions. Okay, so we are going to have e with power of 4t multiplied with the Heaviside functions, like that. And then this will be t. The a is 2, so minus 2. Okay. Oh, the t also changed here. I forgot to change this t. Okay. Because this is supposed to be the t minus a. Okay, so everything needs to be also changed to t minus a. So every time you have an inverse form of a functions and then multiply with an exponent, okay, and usually the variables, they are having the same variable here. Okay, well, it could be any variable, but usually we are using as. If you could identify this, then every time you see this form, then you need to see that we will have some functions that multiplied with the Heaviside or unit step functions. Okay, this is example number 1. Number 2, let's say we have a Laplace inverse of s, okay, over s squared plus 9 multiplied with e power of negative pi s over 2. Okay. Now, as usual, we could finally, well, try to identify first. The a is pi over 2, okay? And this will be our f, okay? And we could start taking the just this s over s squared plus 9, which this is a cosine, right? So we could take this as a cosine. 9 is 3 squared, right? So cos 3t, okay? And then final result is cosine 3, and then exchange t. Okay, so t need to be exchanged with this a, t minus pi over 2, and multiply with the Heaviside, also t minus pi over 2. So every time you identify a functions, and then it's multiplied with some e with power of negative something, and then we have variable in those power, then you could identify this as the second translation theorem. Okay, the inverse second translation theorem. Okay. Okay, there's another alternative theorem. Okay, we can rewrite the theorem in the previous sections with a new methods. Okay, so we could write with some substitutions. Okay, so let u is equal t minus a. Okay, let me write first the previous theorem so that you can have you can compare with. Okay, so previously we write that Laplace inverse we could write this as f t minus a, and then heavy side t minus a, right? Okay. Now, if we could let u is t minus a, okay, we substitute u as a t minus a, we can obtain that. Let me write Laplace. Let's say let me write as g of t, okay, g of t. Let's say the name is g, and then Laplace of t minus a. Okay, this is equal. Let's put on the definition of Laplace and multiply with e with negative st, g of t dt. Okay, now we substitute this u, so t is u plus a. Okay, so we could take that as integrations. And this will be 0, infinity, e, this is from the definition before, and negative s, t will become u plus a, and then g, u plus a, and then du. Okay. And we can conclude that the Laplace of g of t, heavy side, t minus a, is equal e negative a as Laplace of g of t plus a. This is another alternative forms. All right. Now, this is quite helpful. Okay, if you have a different form, like these examples here, they are all, you can see the patterns like directly, right? So if for example, let's take our time for taking Laplace of t squared, heavy side, and then t minus 2. Okay. Now, we could, like, taking this Laplace, write down all the, we could write down all this plus 4 t minus 2 heavy side, t minus 2, and then plus 4 heavy side, t minus 2. This is, I'll write the final results as well, but actually you need to prove this to be correct. And you need to verify, first is you need to verify that the t squared is this, okay? So it is quite messy. Well, you need to rewrite the t squared as these long expressions, okay? So this is, if we take our time to prove. So yeah, you could see that, okay, this is correct. Then we are going to use this expression, this expansion here, as in our Heaviside form. Okay, so we could write down all of this. Okay. So we could write from this part for this one, and for this part is this one, and the last one is the constant form, and multiply with the Heaviside also. Okay. So when we multiply with the Heaviside like this, we are going to, if we Laplace and multiply the Heaviside, then we have to multiply all this. Okay. So it is quite tiresome because you need to provide the proof that this t squared is this equal this expansion. However, if we let me write once more. If we take the alternative form, t squared Heaviside t minus 2. Okay. Now we identified. So first is this A. Okay, we can identify it as this A, right? So first, that is what we are going to do. So this is 2. So A is 2. And G of t is this one. Okay. Then G of t is t squared. So then we could just write precisely as this expressions. So e to the power of negative as Laplace t plus 2 squared. Okay. Oh, why I'm writing a, it should be 2. So negative 2s. Okay. Now we could Laplace and expand the form inside, and we can Laplace each forms, and it is way more easier, rather than you need to put down all these structures, huge structures. And if we did this, then it's simplified, right? And this will be 2 over s cubed plus 4 over s squared plus 4 over s. And this is actually similar to what we have here. So if you think from this part, so we could take this one by one, right? We could take this one by one. Let me write with the blue, light blue color. So this part is becoming 2e negative as divided by, since it's squared, this will be cubed, and this will be 4e negative as, and since it's t minus 2, Heaviside t minus 2, it's a linear, and this will be s squared, right? And the last one is this Heaviside. The Heaviside is just 1 over s, so we could write 4e negative 2s over s. Oh, this should be, I forgot to write, it should be 2. I forgot to write it 2. This one. Okay. If you look carefully, that this is actually the same of what we have here. But I think this way is much better. And this is another alternative form. Okay. Let's try another one. Okay. Let's try another one. Let's say we have a Laplace of cosine t and then Heaviside. Heaviside t minus pi. Now, since we know that this is our g, this is our a, so we could identify that and write down we can write down, since this is t minus, we could write e. Okay, we could write e. Yeah, let me write first with blue color. So e negative pi s, and then Laplace of this will be cosine t plus pi. Okay, I think that is our Laplace. But remember, when we take Laplace of this cosine, well, it seems that this t plus pi is maybe you are not really familiar with. Remember that when you have cosine, this is just a basic math that we did, I think, right? If you take my class in basic math. So if the cosine is on the third quadrant, t plus pi, then it will be a negative, right? So cos t plus pi is negative cosine t. So we could just use that theorem to just solving this. So that it will be negative, so negative I will put here. So this is Laplace of cosine t. And then simply, this is just negative. Well, we could write this first, and then s over s squared plus 1, and that's it. Okay. Okay, let's say we are going to take example on initial value problem and using the form that we just did, the second translation, okay, and with the alternative form, okay. Or yeah, I think we could start with just initial value problem. So let's say we have this DE, differential equations. And the F is a piecewise, which is pretty interesting because with piecewise, it means that we are going to take the expressions with the expression of the Heaviside, right? The Heaviside or unit step functions. Okay. So we could write the F, okay, as a 3 cosine t. And because of the, when it's interval 0 to pi is 0, then we need to have the Heaviside t minus p or pi. Okay. So cosine t, yeah, okay. All right, and then we take Laplace. Okay, we take Laplace. So Laplace of, or maybe let me write completely, y prime plus y equal 3 cosine t, and then Heaviside, and then take Laplace. Okay, let me write with this. Take Laplace. So we could write one by one. So Laplace of y prime plus Laplace of y, and then 3 Laplace of cosine t, Heaviside t minus pi. Okay, this is supposed to be having that bracket. Okay. Okay, and so basically, our goal in Laplace transform is to solve the differential equations, but there are some structure, some forms that probably we need to think more on how to make the how to get the solutions easily. Okay, But the idea is still the same. The idea, we take the Laplace, we solve the Laplace, and then we go back to the inverse so that we are going to have the final result in terms of t. Okay. So we take Laplace, make it in algebraic formula, algebraic operations in the variable s. So maybe let me help you to understand. Okay. So Laplace, so differential equations. So take Laplace. So this is we usually using t variable. So take Laplace, and this will be algebraic, right? We can operate as an algebra, and then this is in variable s. And then we take Laplace inverse, or maybe let me write in a more clear way. So after this is solve the algebra. Okay, solve the algebra, and then take inverse for that Laplace, and we are going back to t. Okay, and this is the solution that we want. Okay, but in the middle, how to solve this algebra, how to do the Laplace transform, there will be some cases where, like this functions, like here we have the piecewise, and with piecewise means that we could use more reasonable functions that could be evaluate easily, which is we could take the f as this, and we know that we can Laplace this with our form before compare with the previous sections. Okay, so what we are doing now is take Laplace of all this. Okay, so first is Laplace of y prime is s capital Y, and then minus, okay, we don't really have too much complicated, or maybe it is supposed to be very simple. Okay, supposed to be very simple. And then Laplace of y is just capital Y s. Okay, now this part, as we know, this pi is our a, right? And cosine t is s over s squared plus t, right? The Laplace. Okay. Or we could say this our f, right? Of ft. So we could write that this will be we could take this as in usual, which one here, we could take the same results here. I think we could just copy this. Let's just copy the same. We could take that, or maybe let me just write negative 3 e negative pi s, and then s over s squared plus 1. It's the same thing. Okay, I'll just rewrite the structure. Okay, and then we solve the algebra, solve the s, or maybe let me write one by one. And then y0 is 5, so this is 5. So this will be minus 5 equal all of that. Then we could take down a little bit and paste to be this one. And then we could solve as usual using the partial fractions. So this is 5 over s plus 1 minus 3e negative pi s, and then s, and then this will be s plus 1 s squared plus 1. Okay, and we need to take the partial fractions. So we are going to have, I believe, this part here need to be taking the partial fractions. So let me write maybe a little bit here to give you. I think let me just write -3 here, and we can just concentrate inside here. So let me write this is e negative pi s and s, right? Okay. Okay. Okay, I think, yeah, I think we can try to do partial fraction within this one, the inside one, inside the bracket. So take partial fractions, so s plus 1, and then plus this s squared plus 1. And this is irreducible, so we have a and then b s plus c, right? Yeah, can start taking that. This is a plus bs plus c, and then multiply with s plus 1. And this is supposed to be s e negative pi s, like that. Or I think we could take out this. I think it's still okay to make it very simple. 3e pi s, okay? Yeah, I think we can solve this. So as squared plus a plus bs squared plus cs plus bs plus c equal s. So s squared is a plus b plus b plus c s and plus a plus c. Okay, very nice. So a plus b is 0, b plus c is 1, a plus c is 0. Okay, I think we can solve. Let's take minus. A minus c is minus 1. So a minus c is minus 1. Let's use plus. So 2a is negative 1. Okay, right? So a is negative 1 over 2. B is 1 over 2. C is 1 half plus, yeah, negative. So this is half, a little half. Okay, I think it's quite good. So this will be 5 over s plus 1 minus 3e negative pi s. And the whole thing here is a is negative. Okay, so we could write negative 1 over 2 and then s plus 1 and then plus b is half. I think we can separate that part, half s and then s squared plus 1 and then plus half and then s squared plus 1. Okay. Now we take the Laplace inverse, or maybe let me take the more clean form. It's 3 over 2 This is negative, and put all with e, okay, because we want to make the connection to the heavy side, so we need to multiply with e. Okay, and then we could start to look at one by one. So for this, we take Laplace inverse. Let's say for s plus 1, e negative pi s is e negative t minus pi, and then heavy side t minus pi, right? You could write like that. This e is from here, from the e, as usual, the negative at, as we mentioned before in the, I think in the early Laplace inverse. And then because of this a, then we have the heavy side with t minus a, and we also need to change this, becomes t minus pi. Okay, so we could start with the, well, if you maybe not really remember, I think we could write also here 1 over s plus 1 is e negative a t, right, or negative t. And then because of a, then you need to change the t minus pi, both of this, okay, and then heavy side, okay. And then Laplace inverse of 1 over s squared plus 1 e negative pi s, this one. This is equal, this is from sine, for 1 over s squared plus 1 sine t, right, sine t. So sine, and because of this a, that one, so we have t minus pi, okay, sine t minus pi, and then heavy side t minus pi. Okay, lastly, the middle one I forgot. Let me write here. Laplace inverse of s over s squared plus 1 e negative pi s, okay. This is going to be cosine t minus pi, heavy side t minus pi. Okay, I think I need to give space about here. Okay, and I believe after we got all that, then we can solve for the yt. So we could just solve for yt. I think the first one here is supposed to be easy, right? Just s plus 1, similar with this. So we have the e, right? Okay, I will give that opportunity for solving this final structure to you. You could review, like, from the very beginning how the Laplace works. Okay, the idea is the same. So you need to solve the dE, take Laplace, make an algebra, solve the algebra, take the inverse, okay, and that will be your solution. But in solving this algebra or taking the Laplace, there will be several techniques, especially you need to identify. Okay, like for example, you could use now the heavy side. Okay, when you have, especially the piecewise, if you can identify the piecewise functions, you can use the heavy side. Okay, instead just the normal Laplace and Laplace inverse. Okay, and yeah, I think that's it. I think we need more maybe practice. The other sections aside from this is yeah, I think the derivative of transform, but I think maybe we are going to skip that. Okay? And we go directly to Dirac delta. Okay? So it's supposed to be 4.4, the additional operational properties, but I think I will skip that part. But we'll see, Okay. But for now, we could just stop here. Okay, the Laplace for the at least the translation theorem, the second translations, and Laplace inverse of it. Okay. Okay, I think that's it for today's class. Okay.